Well, the Doppler effect is going to get its own little recording, and then that'll take care of section 11. The Doppler effect is a change in the wavelength or the frequency, either way you want to look at it. Those things get changed when the source of the wave is in motion. To kind of illustrate that, I said, well, let's imagine that there's some sort of an insect standing, bugs can walk around on water. It's a matter of the surface area to volume ratio. They don't weigh very much compared to the amount that they touch, the area that they bear against the water. So anyhow, there's this bug walking around on a pond. And let's say that it's, I don't know, flapping its wings up and down, or something like that, that every time they come down, it makes a little splash in the water and creates a wave. Now, if the insect was just remaining stationary at one point, these waves radiating outward from its location would make a bunch of concentric circles. But what if the insect is moving at the same time that it's creating these waves? Well, when I drew this picture, I didn't want to take quite enough space to draw this entire circle, but this outermost circle is centered on that point right there, because the idea is that's where the insect was at the moment that it sent out that wave. So the wave would be centered on the point that it came from. Well, the bug's in motion. By the time it sent out the next wave, it was here. And so this circular ripple on the surface of the water is centered on that point. And the bug continued to move. It's moving along this dashed line here with a constant velocity. So when this wave was created, when the bug made that little splash, it was here, and now it's located here, and any moment now it's going to send out the next wave. So the thing to notice is that instead of having concentric circles, that the waves are bunched up closer together in front of the bug and stretched out farther apart behind it, and this change in the wavelength that you get when the source is in motion is the Doppler effect. Maybe most familiar in the case of sound. Here at the college, sometimes you'll hear the trains whistling for the crossings, and if you're, like you get a bad parking spot at the back of the parking lot, and it takes you all morning to walk into the building, and by the time you get here, you've heard the train cross Seven Springs Road, and then it's made it to the next crossing over there, just the other side of the thruway. Well, of course, the train's not coming straight at you, but it's got a component coming, assuming it's an eastbound train, it's got a component that's toward you as it approaches the one road, and it's moving more or less away from you when it gets to the next one, and you'll hear a difference in the pitch of the whistle, higher pitched as it's coming toward you, lower pitched as it's going away. Or if you're just out walking around somewhere and a little airplane flies over you, you can hear a change in the pitch of the engine, higher pitched as it's coming toward you. Now, here the thing is complicated because we're right next to the airport, and maybe the pilot really is slowing down the engine as it gets ready to come in and land. But if you're just out walking around someplace miles from the nearest airport, airplane goes over you and it sounds like the pitch of the engine decreases. Well, it doesn't sound that way to the pilot. It's the Doppler effect. Higher pitch as it comes toward you, lower pitch once it's moving away from you. Because in front of you, a shorter wave, or in front of the airplane, a shorter wavelength corresponds to a higher frequency, and a longer wavelength corresponds to a lower frequency. Just how much does the frequency change? Well, of course, you knew there was going to be an equation coming sooner or later, right?
Now, this is the other place in section 11 where I thought I could be a little less long-winded than I was when I made the recording last year. The Doppler effect. So as I probably just got done saying a moment ago in the older recording, you've got the source of a wave in motion, and because the source is moving, the waves get squashed closer together in front. That's a shorter wavelength in front of the bug, shorter than it would have been if the bug was stationary, and a longer wavelength behind the bug, longer than it would have been if the bug was stationary. So as far as notation goes, we're going to use the Greek letter lambda for what the wavelength would have been if the source was stationary. Lambda prime is well, if you're in front of it, that's the shortened wavelength. If you're behind it, that's the lengthened wavelength. How much is it lengthened or shortened? Well, the wavelength, say you're in front here, for example, the wavelength gets shortened by the amount that the insect moved between getting off one wave and the next. How far the insect moves during the time of one period would be its speed times that much time. Distance equals speed times time. So the wavelength in front gets shortened by the distance moved by the insect. So in front of the bug, lambda prime equals the unshifted wavelength minus this thing here. Behind the bug, the wavelength gets lengthened by an amount equal to the distance that the insect moved. And then what I did in the old version of the recording is I took this expression for how much the wavelength gets changed, and I did a bunch of substitutions, and I did some algebra to show what, in the end, it shows you what the shifted frequency looks like. See, the frequency is going to be higher here, higher than it would be if the insect was stationary, as those shorter waves will go by you more frequently than they would if they were longer. Back here behind it, those longer waves will go by a certain spot less frequently than they would if the source was stationary. So, you know, F equals V over lambda and T equals 1 over F, and you put it all in and you stir it up and you pour it out, and in the end, it's the thing that you'll see in a moment written on the blackboard when I go back to the older video. So cutting that out probably saves about 8 or 10 minutes, which I imagine you're probably grateful for. Let's see.
That is what you will find written on your formula sheet. Once again, as it's all written out here on the handout, you know, the note packet. VO, O for observer, the speed of the observer. S for source. You know, if it's a car blowing its horn, that would be the speed of the car. And the V with no subscript is the speed of the waves. Okay. As far as all these plus and minus, minus and plus, source might be moving, the observer might be moving, or they both might be moving at the same time. Whatever's going on, if it's bringing them closer together, you use the signs that are on top, okay? If the source and the observer are moving toward each other, you want a plus here and a minus there. If whatever's going on takes the source and the observer further apart, they're going away from each other, then you go with the signs on the bottom, minus and plus. So that's what all of that's supposed to mean. And we have an example. After I've run through that will put section 11 to bed. This is more trouble than it's worth for just one line worth of writing, isn't it? But come on. There we go. So you're standing at the side of the road, and a car is, you went out to get the mail or something, and as a car goes by you, it's blowing its horn. As it approaches, you hear a frequency of 500 cycles per second. And after it's passed you, and now it's, gotten far enough down the road that it's basically moving directly away from you, now you hear 400 hertz. So based on that, you can determine the speed of the car. This actually is a variation on how police radar gets your speed. I mean, they don't train police officers to have perfect pitch, so that if somebody drives by blowing if they're lucky enough that somebody's blowing their horn, they can figure out your speed from that. Rather, they've got that little radar gun sitting on the side of the car, and it shoots little pulses of microwaves at you. And it's a little bit like how the motion sensors work. They're still set up in the lab here. Remember the air tracks? They send out the motion sensors that we use sound waves. Radar uses microwaves, very short radio waves. But it's the same basic principle. You send out a pulse of some kind of waves, and then the echoes return. The units there with the air tracks just measure the delay time and get the distance to the glider that way. But the police radar is set up in a way that it can compare the frequency that it's sent out to the frequency it gets back. And if those pulses of microwaves bounce off of a moving target, there will be a Doppler shift. The frequency they get back is not quite the frequency they sent out, and it's able to determine your speed from that. So this doesn't involve any kind of police officer or radar unit or anything like that, but a lot of the same principles are involved. Astronomers get a lot of mileage out of the Doppler effect. They rely on that rather heavily, because you look at the lines in the spectrum of a star or a galaxy or something like that, and from the Doppler shift in the wavelengths of those spectral lines, they can determine how things are moving around up there in the sky, which is frequently, well, that's one of the ways they determine, and maybe I want to point it at me so I can wave my hands around. That's one of the ways they determine the existence of planets around other stars. There's, I think maybe at this point, been maybe 1 or 2 cases where they've actually been able to get some sort of an image of a very faint planet next to, you would need a big planet, a dim star, and a lot of distance between them. I think they managed to image such a thing once or twice at this point, but it's mostly indirect evidence. There are a couple of techniques that are used, but in one of them, used the fact that if you've got these two bodies orbiting around each other like this, that the star will go toward you. Well, actually, of course, there's a motion across the line of sight also, but as far as the radial velocity goes, the star goes toward you and away from you, and toward you and away from you, because of this planet tugging on it as they orbit each other. And you can see the spectral lines going back and forth over a period of time, and that gives away the presence of an unseen companion. That particular method is somewhat biased towards finding very heavy planets, because they, well, in particular, very heavy planets orbiting very lightweight stars, because that makes the motion more easily observable. But anyhow, there are a number of applications that the Doppler effect can be put to. But to answer this question, first of all, when the car is approaching, maybe I should start out with this. A popular way of doing a question like this one wrong, because there's one that's very similar in the homework, I'm sure, is, you've got the 500 hertz and the 400 hertz, and somebody takes this formula because, of course, the way to approach a physics course is to look for a likely looking formula and then throw numbers at it and hope for the best. So they get this formula and they put the 500 in for one of these F's and the 400 in for the other one. No, sorry. Do that, you're having a bad day. Both of these numbers are shifted frequencies, okay? As the car is approaching you, you're hearing a pitch that's higher than what the driver, F is what the driver hears. That's the unshifted frequency. That's what you would hear if the car was parked. As the car approaches you, the 500 hertz has been shifted upward from that. And as it drives away from you, the 400 hertz has been shifted downward from that. And so you have to write this equation twice, because both of the frequencies you were given are F prime, okay? You have to write it once for when the car is coming towards you, and another time for when the car is going away. And if you were guessing, well, then probably F is right in the middle, 450. No, I mean, that's not terribly far off, but it's still wrong. I believe the question doesn't ask for this. I believe F turns out to be 444 hertz, not 450. But anyhow, you have to write the equation twice. Once for the car coming toward you, once for when it's going away. So approaching. First of all, speed of the observer, you're just standing there by your mailbox. So the speed of the observer is 0, and that part of it's gone. With the car coming toward you, you want the top sign. So that's the minus. Put the minus in there. We know V, actually. V is the speed of sound, because it's sound waves in this question. So I could put 343 in there now. And I don't know, maybe that would be a good idea, but the way I was looking at it is I'm going to have to write a number of lines of algebra before I get to where I'm going. And as I work my way through that, it's going to be easier to write, 343. That's 3 things to write. V is only 1 thing to write. So I thought I would just keep calling it V for a while. But keep in mind, that we know that. We have two unknowns here. The frequency, the unshifted frequency, and the speed of the source. Vs is what the question asks for. We don't know F, we also don't care about F. So after it passes you, it's going to be the same sort of thing, except now it's going away from you. So you want to go with the sign on the bottom. We'll have the plus sign down here rather than the minus. And so we have a system of two equations in two unknowns. Remember, V is actually 343. I can fill that in anytime the mood strikes me. There are two things I don't know: the unshifted frequency, the frequency the driver hears, and the speed of the car. And so there's different ways you could work your way through the algebra. If you were working on this and did it a little differently than how I'm going to do it, that might be just as good. But what I did anyhow is I used this to obtain a substitution for F. F equals 400 times, and then, you multiply both sides by that, and now it's on top. And you divide both sides by that, and now it's on the bottom. So F would equal 400 times this flipped upside down, like I wrote here. And then I'm going to stick it in here to eliminate F so that I've got just one variable instead of two. Okay, I guess that's still on the camera. Yeah, I better slide this over a little bit at this point. So 500 equals F. Well, F is equal to this expression here. So I put that expression where the F used to be. So F times V over V minus Vs. This is F between here and here times V over V minus Vs. And when I do that, V over V cancels out, which helps things a little bit. And what I'm going to do next is combine these two constants. I'm going to divide both sides by 400, so I've got 500 over 400. really the physics was done once I had gotten these two equations written down. And from there on, it's all math. And as I said, there are various routes you could work your way through the math. I thought this went as quickly as anything, but another possibility is you could divide the one equation by the other and make F drop out that way. That would be an alternate way of working your way through the math. Anyhow, 500 over 400 is equal to 1.25. And I'm going to take the V minus VS and multiply both sides by that. So I've got okay, 500 over 400 is equal to 1.25, and then multiply both sides by that quantity to get rid of the fractions, you know. And then what's left is to combine the like terms. I've got a 1.25V and another V there, and I've got a 1.25 VS and a V. And I'm getting pretty boxed in down in that corner. I think I'm going to go over to the left-hand end of the blackboard here again. But I am within spitting distance of having this thing finished. So let's see, the last thing I wrote over there was 1.25 times okay, so that's where I left off over there. Distribute the 1.25. And then rearrange it so that the like terms are together. Subtract V from both sides, add 1.25 VS, both sides. That minus that is 0.25 V. That plus that is 2.25 VS. Okay. Remember I said V, we've known it since the beginning. That's the speed of sound. And I could have plugged that in at the beginning. It seemed like less writing if I called it V for a while. So 0.25 times 343 is 85.75. Divide, and we have the answer. 87.75 divided by 2.25. 38.1 meters per second. So based on the Doppler shift in waves that are coming from this car, it's going just about exactly 85 miles per hour. And that gets me to the end of section 11. Till next time, have a good however long it'll be.